So this video is about special right triangles, and you'll be taking these notes on page 37. Basically, there are two special triangles that you're going to be using a lot in your future, and I want to show you where they come from, how the sides are related, and have some practice problems done with you. So there's a lot of triangles all over the place in life, in engineering, and you want to be able to locate those triangles. Isosceles triangles, right triangles, come up the most often. It has to do with the way weight is dispersed with an isosceles triangle to balance things out. Right triangles certainly do a good job with balancing out forces. So an isosceles right triangle comes up a lot. Now, where do certain special triangles come from? They come from our simplest shapes. Equilateral triangle and a square are probably the simplest polygons you can find that have as much symmetry as you can imagine. They have all their angles equal, they have all their sides equal. We know that the angles of an equilateral triangle are 60 because the angles add up to 180 and there are three of them and they're equal. And we know that the angles of a square are 90 degrees. You've known this for a long time. How do you get special right triangles? You simply cut those guys in half. So you take your equilateral triangle and you drop a height straight down, perpendicular, splitting the base into two equal parts and splitting this angle up here. That was 60 degrees. It's now 30 here and 30 here. So the right triangle on the left is congruent to the right triangle on the right. And I can split my square diagonally from corner to corner, and you can see a isosceles right triangle here that is congruent to the isosceles right triangle up there. So they simply come from our most familiar simple polygons, equilateral triangle and the square. That gives us our special right triangles. Now they're named by their angles, 30, 60, 90 triangle, 45, 45, 90 triangle, simply because mathematicians have no creativity in naming things. Now, we're going to be looking at the relationship between the sides. And so you've got to remember that in our equilateral triangle on the left, when we split it into our special right triangle right here, we split the base. So if this piece here is x, this piece over here is also x. And the full length is 2x. So that means this full length here is 2x. So in this right triangle on the left-hand side, my hypotenuse is 2x, and this short leg is x. In my half of a square, the sides of a square are equal. So that's easy. Whatever this side is, that side is also. What we don't know is what's the hypotenuse. We know the hypotenuse here is twice that leg, but here we don't know the height or the long leg of the special right triangle. So we're going to use the Pythagorean theorem to find those remaining sides. Let's start with the isosceles right triangle. Let h be the hypotenuse. It's going to equal to the leg squared plus the leg squared. But the legs are equal, so you can combine those. And then you can take the square root of both sides. So your hypotenuse is going to equal the square root of 2y squared. Well, you can break that up. Take the square root of y squared, gives you y, and then simply rearrange it because we usually put the number in front of the square root part. So what this is telling me is that if I have an isosceles right triangle and my leg is y, then my hypotenuse is going to be y times the square root of 2. And that's true for any 45, 45, 90 triangle. Remember that every triangle that's a 45, 45, 90 is going to be similar to any other triangle that's 45, 45, 90. And so the sides are all going to be in the same proportions. So again, to summarize, and remember you can always pause this to write notes in your notebook, for any 45, 45, 90 triangle, the legs will be the same. And if the legs are, say, y, then the hypotenuse is y times the square root of 2. Now let's do the same process on our 30, 60, 90 triangle. Remember, we said that if this short leg was x, that the hypotenuse would be double that. But what is going to be the long leg, or the height of my original shape? We're going to call that h as we do our computations. Again, using the Pythagorean theorem, short leg plus long leg, or short leg squared plus long leg squared, will equal the hypotenuse squared. Be careful when you square a product. Combine like terms by subtracting x squared from both sides. Take the square root of both sides. Remember that you can take the square root of x squared, you can take the square root of h squared, but the square root of 3 is irrational, so we just leave it as the square root of 3. So what we've discovered is that if I have a 30, 60, 90 triangle, whatever the short leg is, the long leg is going to be that number times the square root of 3, always. So again, to summarize, for any 30, 60, 90 triangle, if the short leg is x, then the long leg will be x times root 3, and the hypotenuse will be twice the short leg. You want to summarize this in your notebook on page 37. Remember, you can pause the video as you need. Remember also that in an isosceles right triangle, if two angles are equal, the sides opposite them have to be equal. That's why this and this are the same. And the hypotenuse is the leg times root 2. In a 30, 60, 90 triangle, none of the angles are the same. The smallest angle is 30, and its opposite the smallest side. The middle angle is 60. Its opposite, x times the square root of 3. And the largest angle is the 90-degree angle, and its opposite, the longest side, the hypotenuse. Just for your reference, the square root of 3 is about 1.7. So if I start out with x, I multiply it times 1.7, or I multiply it times 2, certainly when I multiply it times 2, that'll be the longest side in the triangle. And the hypotenuse is always the longest side in a right triangle. Now we're going to practice this. Here's your 30, 60, 90 triangle. In this case, I've given you the shortest side. What's the hypotenuse? Remember the rules. The hypotenuse will be 8. Here's another 30, 60, 90 triangle. The shortest side is 7. We know that the shortest side is half of the hypotenuse. So my hypotenuse is going to be 14. And my longer leg, which in this case is y, is going to be the short side times root 3. So this side is going to be 7 root 3. Do not be alarmed if the triangle gets rearranged. It's still a 30, 60, 90. You can still locate the shortest side by finding the smallest angle and looking opposite it. You can locate the hypotenuse by finding the right angle and looking opposite it. So in this case, my hypotenuse is given, and it's 10. The hypotenuse is twice the shortest side. So what's the shortest side? It would have to be 5. And the long leg is just square root of 3 times the short side. So what is the long leg? 5 times the square root of 3. Do the same process again. I've given you the hypotenuse. It's opposite the right angle. So what is the shortest side? It would be 8. And the long side? It would be 8 times root 3. Now I've given you the long leg. It's opposite the 60-degree angle. It has the square root of 3 in it already. It's short side times square root of 3. So that tells me that my short side must be 7. And my hypotenuse, if it's double the short side, must be 14. Now this one is a little bit harder. You're going to need to write things down. Because in this case, my longer leg is opposite the 60, but it doesn't have a square root of 3 in it, even though we think it should. So we're going to have to do a little bit of algebra to solve for x, which is my shortest side. You know that the short side times root 3 equals the long leg. So you simply divide both sides by root 3. But we don't usually leave a square root of 3 in the denominator. We need to get rid of that radical in the denominator. So we do a process called rationalizing the denominator. This fraction here that I'm circling is really just the number 1. It's the same thing on top and on bottom. But what I've put on top and on bottom is that irrational square root. I put the square root of 3 in both places. So when I multiply across on the bottom, I'll just get a regular 3, a nice rational number. I'll get an irrational number on the top, but that isn't as troublesome. And now I have a rational bottom and a rational top. I can simplify those. I can divide the 3 into the 15, so I get just a 5 root 3. So now I no longer have a fraction, and I don't have an irrational number in my denominator. So we like that better. But don't forget, we also want to find our hypotenuse, which is always twice the short leg. So if I double this number, I get 10 root 3. I double the 5 to get the 10. You don't double the root 3 because essentially you've already doubled it because you've doubled the 5. Here's another one, very similar to the last one. We're going to solve it the same way. Short leg times root 3 equals 6. Divide both sides by root 3. Rationalize the denominator by multiplying by root 3 over root 3. You've got a cleaned up denominator, so you can divide it into the nice, clean, rational numerator. 3 goes into 6 twice. So my short leg is 2 root 3. And my hypotenuse is double that. Now let's look at those 45, 45, 90 triangles, those isosceles right triangles. They have 2 legs that are equal, and the hypotenuse is square root of 2 times the leg. So if my leg is 11, my hypotenuse is just 11 times the square root of 2. If my leg is an irrational number, I still just multiply it times the square root of 2 to get the hypotenuse. If they're both irrational, if they're both radicals, you just multiply the radicands, the numbers inside. So we'll do the same thing here. I'm going to multiply the square root of 3 times the square root of 2, and that will give me the square root of 6. Now in this case, I've told you that the hypotenuse is 12 root 2. Well, we know the hypotenuse is x root 2, where x is the leg. So that is just a quick and easy. My leg must be 12, because 12 times root 2 would give me 12 root 2. This one is harder. A times root 2 is going to equal 20. So we want to write that equation, divide both sides by root 2. Once again, they don't like us to leave square roots in the denominator. Has a long history. I can explain it to you in another video. So it's root 2 over root 2 again to rationalize that denominator. Root 2 times root 2 is a nice rational 2 in my denominator now. I got an irrational upstairs, but that's okay because I can simplify the rational parts and I get 10 root 2. So my leg A must be equal to 10 root 2. Now there's many ways to solve this problem, but I'm just going to start out by saying that x times root 2 would equal root 8, just like we've been doing every other problem up till now. Divide both sides by root 2. Now you could simplify this at this point, but let's go ahead and rationalize our denominator just like we've been doing. Square root of 2 times square root of 2 gives me 2. But look, I got the square root of 16 up here, which is 4. And so it all cleans up really nicely. So my leg is 2, which really means that this is 2 times the square root of 2. And it is, because 8 is 4 times 2. So if we simplify this radical, we will get 2 root 2. So to summarize, we've got 2 special right triangles. You need to know the relationships between the sides in them. You need to be able to spot which side is which, even if you've turned the triangle around. You need to sometimes write equations to solve for things, and you need to know how to rationalize your denominators. A lot of topics, but it's really important, and you will use this a lot.